Good day, everyone. We're reviewing Wetzel's Limnology textbook. This is edition number 4, and we're on chapter 11, oxygen, and more specifically, we're looking at temporal variation in oxygen concentration in rivers right now. In nutrient-limited oligotrophic rivers, such as those draining high latitude and high elevation catchments, the temporal variation in nutrient availability can also drive seasonal productivity. In such cases, early spring and fall represent critical windows of opportunity when discharge turbidity, riverbed stability, temperature, and light conditions align to promote high rates of river productivity and thus results in the highest oxygen variability exhibited within a year. In streams influenced by glaciers, high levels of turbulence coupled with reduced light availability additionally limits benthic oxygen production and push oxygen saturation back to equilibrium during summer, the period of maximum ice ablation. Therefore, physical drivers of oxygen dynamics prevail over biological drivers in the period between shoulder season in these high elevation rivers. Annual patterns in aseasonal rivers. 5 Mile Creek in Alabama and San Antonio River in Texas show little seasonality. 5 Mile Creek exhibits large diel variation in oxygen, while the more urbanized San Antonio River shows more erratic behavior. This stochastic oxygen pattern is characteristic of river ecosystem draining highly urbanized areas, subject to more flashy hydrograph. Short-term episodic hydrological events such as storms, dampen regular oxygen oscillations through a combination of increased water volume, shading due to turbidity, and removal of burial of photosynthetically active biomass. The intensity of hydrological disturbance thus determines the duration for oxygen dynamics to recover back to baseline conditions. For example, recovery times for both primary production and respiration are expected to be longer after large floods that disturb riverbeds compared with small floods that only generate turbidity without disturbing the riverbed. In addition, storms that can also lead to episodic hypoxia coincide with pulses of low oxygen water or increasing organic matter from anthropogenic waste or natural storage. Diel patterns. Diurnal cycles in solar radiation impose a well-known periodicity on river biogeochemical processes, creating diel patterns for many solutes and gases, including nutrients, dissolved organic matter, metals, and dissolved oxygen. Photosynthesis increases oxygen concentration on a diurnal basis, particularly in relatively slow-moving rivers. In productive rivers, diurnal oscillation in dissolved oxygen concentration are even more magnified. For example, in a wide, unshaded reach of an urban tributary draining the New Hope Creek watershed, hypoxia occurs daily at night, with diel oxygen concentration oscillating as much as 10 milligrams of oxygen per liter per day, which will correspond to about 130% saturation, in response to very high primary productivity. Heterotrophic and autotrophic respiration at night results in repeated oxy-hypoxic cycles. At the watershed scale, land use is a major determinant of a river daily oxygen dynamics. Land use controls light availability within channels and alters the intensity of hydrologic disturbances as well as the delivery of limiting nutrients and organic matter. For example, forested catchments are typically characterized by dense canopies surrounding stream channels. Light availability for photosynthesis in those rivers is limited, resulting in damped diel cycles of dissolved oxygens. For other types of land uses, for example, open canopy grassland and croplands, high nutrient inputs and unlimited light availability make aquatic primary production and diel oxygen cycles more likely. Other processes also vary at sub-daily timescales and drive diel changes in dissolved oxygen, including light-induced photochemical oxidation of organic matter. Diel changes in discharge and associated scouring, and lateral export of water with various amounts of oxygen from adjacent terrestrial environments. Regardless of the driving forces, the magnitude and extent of diel oxygen changes in running waters remains poorly studied except for well-studied cases. Changes in river oxygen concentration at decadal and continental scales. So before we get here and go through that, let's look at these figures here. So I think these are like the last two that we need to look at. So let's look at these figures. Figure 11-10. Diurnal cycles of dissolved oxygen concentration in a nutritionally balanced and a eutrophic river. Inset represents major biophysical factors driving changes in the amplitude of diel oxygen cycles. Higher nutrients inputs in rivers increase the amplitude of the diel cycles by subsidizing autotrophic primary production. So autotrophic is primary production is production that is occurring at the level of the river, in the river itself. All right, so here we have on the y-axis we have the concentration of dissolved oxygen in milligrams per liter, and on the x-axis we have time, and we are looking at like about a day and a half here. So starting at midnight till about midnight, and then to 4 p.m. So this is sunrise, sunset, and sunrise. And then in this inset, we are looking at the biophysical factors driving changes in the amplitude of the oxygen cycle. So nutrients, light, scour, and grazing. So nutrients increase. So nutrients increase in this direction, upward, as well as light. And then scour and grazing decrease in that direction, downward. So at sunrise, we are seeing an increase in the oxygen concentration right at sunrise, and post solar noon at about 4 p.m. we are seeing the highest concentration of oxygen. That is due to the fact that we are inputting, in this case, this is a eutrophic river that is nutritionally, nutrition balance and a eutrophic river. So we are like looking at, so we're probably looking at two rivers, okay. So the dashed line is the nutritionally balanced river, and then this is the eutrophic river. So two different rivers on the same graph. So eutrophic river is where we are inputting some nutrients into the river. So as we are saying here, we're subsidizing autotrophic primary production. So by doing so, we are changing the amplitude of the oxygen concentration. You can see that the oxygen concentration is way lower than in the nutritionally balanced oligotrophic river, where that is only supported by autotrophic nutrient production. So the amplitude of the concentration of oxygen is not as high. And then we're also seeing like a process, like in terms of oxygen concentration, that is driven by the daylight. So this is a daily based oscillation, like your typical bell curve. Okay, so then here, figure 11-11 is example of daily trends in dissolved oxygen content measured over 48 hours in three rivers, draining contrasted land use types. Light and dark periods are represented by white and gray rectangles, respectively. So this is the dissolved oxygen in percentage in saturation. So where we have like 100% saturation of dissolved oxygen right here, that value on the y-axis, and on the x-axis we are looking at time in hours, and so therefore we're looking at the alternation of daylight in the white compared to the gray, which is the night. And then here we are looking at the different types of rivers with different types of draining different types of land use. So one is the forest. So the forest is this continuous line. The dashed line short is the grassland, and then this is the cropland in a long dashed line. So first is we are not seeing much variability in dissolved oxygen concentration for a river that is draining a forest. and we are seeing the highest for a river that is draining a grassland. And that is kind of surprising because you would expect that for cropland, where we are inputting very likely fertilizer into the cropland to boost up yield, and some of that fertilizer potentially would end up in the river and drive productivity, as we saw above. It would make the river eutrophic. So there might be other mechanisms here. And then in terms of the shift, also seeing a shift in the percentage net saturation is not exactly the like synchronous with between the grassland and the cropland. The grassland peak of oxygen saturation is later than the cropland. And then we are also seeing that the grassland, as we just mentioned, is we are seeing higher amplitude of dissolved oxygen saturation than in the cropland. Okay, changes in river oxygen concentrations at decadal and continental scales. Long-term oxygen data series are key to revealing both improvements and declines in river oxygen content. For example, long-term monitoring data have enabled the detection of a decline in biochemical oxygen demand trends in Europe since 1992, following a general improvement in wastewater treatment induced by the EU Water Framework Directive. These long-term data have also detected ecological recovery patterns of highly altered rivers following sewage abatements. However, data from the Global Rivering Dissolved Oxygen Database, which is composed of 125,158 unique river locations spanning more than 90 countries, show that rivering hypoxia is more widely distributed than had been previously assumed, and more likely to occur in warmer, smaller, and lower gradient rivers draining urban land cover. Despite these advances, larger scale spatial and temporal patterns in dissolved oxygen remain largely unknown. There is still a clear bias toward river monitoring in temperate regions, and several major regions on the planet remain woefully understudied. Consequently, the rivers described in this section are isolated examples, although promising recent studies are rapidly expanding our understanding of river oxygen dynamics. Distribution of dissolved oxygen in lakes. So we're switching here. We're talking about rivers and oxygen distribution in rivers and how it's driven by diet cycles and other factors such as nutrient availability. And then now I'm looking at oxygen concentration and oxygen cycling in lakes. Oxygen concentration in lakes can vary both temporally on diel, seasonal, and annual scales, and spatially on horizontal gradients between littoral to pelagic sites and on vertical gradients with depth. Below, we first discuss temporal variability in oxygen dynamics in dimictic north temperate lakes as an illustrative conceptual model, and then address a broader suite of observed dynamics in lakes of different mixing regimes. On timescales of minutes to hours, oxygen concentration can respond rapidly to meteorological forcing, river inflows, biogeochemical cycling, and plankton populations. There is generally greater variability in oxygen within the epilimnion than the hypolimnion on daily and subdaily scales during thermally stratified summer periods. During the day, oxygen in the epilimnion increases due to the primary production and decreases during the night due to respiration. In productive lakes, photosynthesis during the day can result in epilimitic limnetic supersaturation until there is an evasion of the excess of oxygen to the atmosphere. Mixing events due to storms or inflows can also result in short-term increases in oxygen if surface oxic water is entrained into deeper layers that are undersaturated. Internal stations may also have a measurable imprint on oxygen dynamics at daily timescales by promoting vertical and horizontal advection in surface and deeper layers. On seasonal timescales, lakes can exhibit distinct vertical oxygen profiles, enabling the differentiation of lakes based on their oxygen dynamics. These profiles emerge from physical, chemical, and biological interaction within the water body, and thus limnologists can infer valuable information about a lake's ecosystem functioning from its oxygen profile. It is important to note that the classification of lake oxygen profile is based on profiles collected during thermally stratified conditions. This is because oxygen concentration can be at or near 100% saturation throughout a vertical profile when a lake is mixing, making it thus impossible to differentiate among other profiles during mixing periods. So before we move on, let's look at that figure here, figure 11-12. Idealized vertical distribution of oxygen concentration and water temperature during the four seasons of an oligotrophic and a eutrophic dimictic lake. So one is nutrient rich and one is nutrient poor, and they both turn over twice a year. So the spring turnover, so here we have on the x-axis here, we have oxygen concentration in milligrams per liter. We also have temperature in degrees centigrade, and then we have depth. And on the upper part of the graph here, we have oligotrophic lakes, and then we have eutrophic lakes here. So for both the oligotrophic and the eutrophic lake, the distribution of, so we don't have, so that's right, we don't have the data for when the lake is mixing. So there's no data here. There's no curve. Now it's stratified, and we're in the summer stratification phase. And this is an oligotrophic lake, and we are seeing that the oxygen concentration increases with depth. And then this is the temperature. And so then we have the thermocline here, and then we have lower temperature in the apolymion than the epilymion here. And then for the eutrophic lake, we have somewhat of a different pattern for oxygen. So oxygen is lower, or to almost zero, in concentration at depth beyond the thermocline. And we have compatible concentration at the surface like we do here in the oligotrophic lake. And then the temperature, we have the same curve. So that doesn't change the temperature whatsoever. The only change is the oxygen. Then we don't have any data for when it's mixing. And then in both cases, it appears that both lakes build a nice layer. And I'm assuming this is the representation of the ice. So this is the oligotrophic lake, and we have pretty high concentration of oxygen, as well as the concentration distribution is pretty even between the AP and the apolymion. And where the eutrophic lake, we have definitely still a very low concentration at depth than we do, although not as high in the winter than in the summer, and the same temperature curve for both. And so we still have hypoxic condition in the lake, and that is eutrophic, even in the winter, even with the presence of an ice layer. Okay. So on seasonal timescales, lakes can exhibit distinct vertical oxygen profiles, enabling the differentiation of lakes based on their oxygen dynamics. These profiles emerge from physical, chemical, and biological interaction within the water body, and thus limnologists can infer valuable information about a lake's ecosystem functioning from its oxygen profile. It is important to note that the classification of a lake oxygen profile, lake oxygen profiles, is based on profiles collected during thermally stratified. So we already did that. And so, let's see. Okay, I think this is where we stop. Mixing periods are an important, Mixing periods are an important time for increasing oxygen availability in the bottom waters of lakes, because molecular diffusion is very slow. Generally, the only way for the entire water column to reach 100% dissolved oxygen is for the water column to mix, as occurs during spring and fall turnover. After the onset of mixing, 100% saturation is established relatively quickly, usually in a few days in most lakes. Very deep lakes, however, require a longer period for complete equilibrium saturation, and saturation may not be achieved before the onset of stratification. In an idealized deep lake, the oxygen concentration throughout the water column during circulation is at or near 100% saturation. Once thermal stratification sets up in the summer, in a temperate lake, 4 distinct profiles can emerge: orthograde, clinograde, positive heterograde, and negative heterograde. Below, we address each of these oxygen profiles, focusing on the example of an idealized dimictic deep lake. And that's going to be it for today, and we'll pick it up tomorrow with section ACE, orthograde oxygen profile. Thank you, and I'll see you tomorrow.